Let us reconvene. So now we are gonna lead towards the calculation of the threshold voltage. First, what is the threshold voltage? Going back to slide number 17, the threshold voltage is the voltage required to make the channel between the drain and the source. Or in other words, you can say the threshold voltage is the minimum voltage required to connect the drain with the source by creating the channel of electrons. And the threshold voltage actually has certain characteristics. First, at the threshold voltage phi s, which is the difference between the intrinsic Fermi energy level in the bulk and the intrinsic Fermi energy level at the surface. So the surface potential at the threshold voltage would be equal to 2 times phi Fp, where phi Fp is the energy difference between the intrinsic energy level and the Fermi energy level. So the first characteristic at the threshold voltage is that phi s now is equal to 2 times phi Fp. And the second characteristic of the threshold voltage is that at the threshold voltage we will see maximum depletion width. As you can see over here, above the threshold voltage, the depletion width is not going to increase any further. So we saw a relationship for the calculation of the depletion width, and we know that at the threshold voltage phi s is equal to 2 times phi Fp. So now at the threshold voltage, replace phi s with 2 times phi Fp, and now we see that the formula for the calculation of x dt, or the depletion width, actually slightly changes. Now it's equal to 4 times permittivity of the semiconductor times phi Fp, which is energy difference between the intrinsic energy level and the Fermi energy level divided by charge on electrons, times the acceptor doping, and take the square root of this expression. So the goal is to calculate the threshold voltage, and before deriving the expression for the threshold voltage, let us look at an example. In this example, the acceptor doping is given, and we already know the intrinsic carrier concentration for silicon, 1.5 10 to the power of 10 per centimeter cube at room temperature. We are asked to calculate the maximum depletion width for the given semiconductor doping concentration. So we have a formula for calculating the maximum depletion width. We know that we see the maximum depletion width at the threshold voltage, and we have this expression for calculation of the depletion width at the threshold voltage. But first we need to calculate phi Fp using this simple formula. Vt is the thermal voltage, and A is the acceptor doping given in this example, and I is the intrinsic carrier concentration. And then replace the value of phi Fp, which will result in the calculation of the maximum space charge width, or the maximum depletion width at the threshold voltage. It comes out to be 0.3 micrometers. So now we are actually trying to lead towards the calculation of the threshold voltage. For that purpose, we also need the depletion region charge density. We already have an expression for the depletion region charge density. Qd is equal to square root of 2q and A epsilon Si times phi s. But previously we actually considered the substrate to be connected to ground. But in reality, we are going to discuss it in detail post-midterm. In reality, we actually connect N-type MOSFETs. We actually connect the substrate of N-type MOSFETs to positive potentials, and we connect the substrate of p-type MOSFETs to negative potentials. So in reality, for VLSI circuits, the substrate is not connected to ground. It is connected to a certain potential. So here is the formula for the depletion region charge density at 0 applied bias, or we can also say under thermal equilibrium. At zero substrate bias, not 0 applied bias, 0 substrate bias. And when we bias the substrate as well, then we need to modify this formula for the depletion region charge density. We need to add the substrate bias to it as well in this expression. So now let us talk about the threshold voltage. The threshold voltage actually has some components. For example, look at this energy band diagram over here. So the substrate, in order to create the inversion layer or the channel, we need to apply a voltage which would cater for a few components. First, we know that there is a difference of work functions between the metal and the semiconductor. So the threshold voltage has to cater for this difference between the work function of the metal and the semiconductor. Secondly, we have a surface potential over here. The intrinsic energy level at the bulk minus the intrinsic energy level at the surface. Then we have a depletion region over here, and we know that inside the depletion region for a p-type substrate we have fixed negative charges. So the threshold voltage has to cater for the depletion region charge density. And since we have fixed negative charges inside this depletion region, on the semiconductor side, we would have fixed positive charges in the oxide layer as well. So the threshold voltage has to cater for these fixed positive charges in the oxide. So basically, the threshold voltage has 4 components. Under 0 applied bias, it's equal to the work function difference between the substrate and the metal, and then we add this component which represents the surface potential, and then the depletion region charge density, and then the oxide charges. It's simple to calculate the work function phi GC. It's the work function difference between the substrate and the metal, and we have a simple formula for the calculation of the surface potential. It's equal to 2 times phi Fp at the threshold voltage, and then we have a simple expression for phi Fp as well. Here is the formula for the calculation of the depletion region charge density in coulomb per centimeter square at 0 applied bias. And then we also need to calculate the oxide charges in coulomb per centimeter square. At non-zero substrate bias, which means when we connect the substrate to some potential, for the depletion region charge density, now we also need to add the substrate bias potential in this expression as well. And if we replace QB with this expression, it reduces finally to this form. So now our threshold voltage under non-zero substrate bias is equal to VT naught, the threshold voltage at 0 substrate bias, minus this small term, this additive term. After further simplification, it reduces to this form. Now VT is equal to the threshold voltage at 0 substrate bias plus gamma times, we already know about these parameters, where gamma is called the substrate bias coefficient, or we can also call it the body coefficient, and it's equal to square root of 2 times charge on electrons times acceptor doping times permittivity of silicon divided by oxide capacitance. And here oxide capacitance actually is in farad per centimeter square. So let us consider an example. In this example, we are actually looking at the metal oxide semiconductor at 0 substrate bias. So the substrate is not connected to any bias, it's connected to ground. The gate is made up of polysilicon. The substrate doping is 10 to the power of 16. The gate doping is 10 to the power of 2, 10 to the power of 20. So it's polysilicon gate and it's heavily doped. 2 10 to the power of 20 is heavy doping of the polysilicon gate. The oxide thickness is also given 500 angstrom, or we can say it's 50 nanometers. And the oxide interface fixed charge density is also given. So the number of oxide charges are 4 into 10 to the power of 10 per centimeter square. But in order to convert it into Q oxide, or the charge density, we need to multiply it with the charge on electron. So with these parameters in mind, and we already know the equation at 0 substrate bias is over here. So we have to calculate phi GC and then 2 phi F and then these two expressions. In order to calculate phi GC, which is equal to the work function of the substrate minus the work function of the gate. And we already know the formula for calculating the work function of the substrate, kT by Q natural log of Ni divided by Na. Na is given in this example. It is 10 to the power of 16 per centimeter cube. In I, we already know, roughly 1.5 10 to the power of 10 per centimeter cube. So the value of phi F for the substrate comes out as minus 0.35 volts. Now how about the work function of the gate? So since this is polysilicon and this is heavy doping, if the doping is heavy, it means that the Fermi energy level for silicon now it's close to the conduction band. It either surpasses the valence band or it's almost aligned with the conduction band, not with the valence band. So now it's polysilicon gate and now it's aligned with the conduction band for the polysilicon gate, which also means that now this phi F over here is the energy difference between the intrinsic energy level and the Fermi energy level for the p-type silicon substrate. So it means the intrinsic energy level is at 0 electron volts and the conduction band would be at EC minus EI. If the intrinsic level is at 0, then EC minus EI is equal to half the energy band gap, 0.55. So phi F of gate becomes 0.55 volts and phi GC comes out to be minus 0.9 volts. So we already determined the first term over here for the calculation of the threshold voltage at 0 substrate bias. Now we know the value of phi GC. And we also calculated phi F. So now the surface potential would be equal to 2 times phi F. For calculation of the depletion region charge density, we have an expression. We calculated phi F in the previous slide, minus 0.35 volts. So replace the value of phi F in this expression, and the depletion region charge density is also calculated in coulomb per centimeter square. How about the oxide charges? N oxide is given in the example 4 10 to the power of 10 per centimeter square. But to convert it into charge density, we need to multiply it with the charge on electron. So it results in the depletion in the oxide charge density in coulomb per centimeter square. But in this expression for the threshold voltage at 0 substrate bias, we calculated QB naught and Q oxide, but now we need to calculate C oxide as well, where C oxide is equal to permittivity of the oxide divided by the thickness of oxide. It's actually farad capacitance per unit area and farad per centimeter square. We know for a parallel plate capacitor it would be epsilon times area of the parallel plates divided by the distance between the two plates. But here we are calculating capacitance per unit area, so we don't multiply it with the area over here. The relative permittivity for silicon dioxide is 3.97, multiplied with the permittivity of free space divided by the thickness of oxide is given, converted into centimeters. So now we have capacitance per unit area as well. Replace these values in this equation for the calculation of the threshold voltage at 0 substrate bias. We get a threshold voltage of 0.4 volts. So that means that for 0 substrate bias, we need to apply a voltage of 0.4 volts at the gate in order to form the channel between the drain and the source for the MOSFET. Now, what happens if we connect the substrate to a potential, to VSB? So let us consider the effect of that. And for that purpose, the relationship is given in one of the previous slides for a non-zero substrate bias. Here is the equation in which we need to calculate gamma. So let us first calculate gamma. Here is the relationship for the calculation of gamma. The acceptor doping is given over here. We are going to use the same values as example 3.2. Now gamma comes out to be 0.82, and here is the unit of gamma. Gamma is the body coefficient. For a non-zero substrate bias, replace all these values. In the previous example, Vt naught at 0 substrate bias came out to be 0.4 volts. Replace the value of gamma in this equation. Phi f we already know, plus VSB minus 2 times square root of 2 times phi f. Replace all these values. So now we have an equation for the threshold voltage at non-zero substrate bias as a function of the substrate bias. And let's consider a range of values for the substrate bias in the range of 0 to 5 volts for the substrate bias. We can use MATLAB in order to plot this. So now we see that the threshold voltage now ranges from roughly 0.4 to approximately 1.7. There is a variation of 1.3 volts. At 0 substrate bias, in the previous example, the threshold voltage came out to be 0.4 volts. But now we see that at 1 volt substrate bias, it increases to approximately 0.7 volts. And then at 5 volts, it approximately increases to 1.6, 1.7 volts. Which means that if we apply a substrate bias, the threshold voltage would increase. So there is a price for that. And since here we are talking about a p-type substrate or n-type MOSFET, as I already told you, that for an n-type MOSFET, the substrate is connected to positive potential. So that's why we are increasing, we are using the values, positive potential values for this plot for the substrate bias potential. So far we considered an NMOS transistor. Now let us consider a PMOS transistor. We have the equation for non-zero substrate bias, and for this PMOS transistor all the values are given. The threshold voltage is given, the body coefficient is given, the substrate bias is given, 2 times phi f is given. So all the values are given. Just put in all the values in this equation, and at minus 2.5 volts substrate bias, the threshold voltage now increases from minus 0.4 volts at 0 substrate bias to minus 0.8 volts at non-zero substrate bias. Also, as I told you, for the previous example, that for an N-type MOSFET, we connect the substrate to positive voltages. You can see that in this example 3.3. And now here we are considering an example of P-type MOSFET. So as you can see that for P-type MOSFETs, we connect the substrate to negative potentials. So my point is already validated over here in these examples as well. Why do we connect N-type MOSFETs, the substrate of N-type MOSFETs to positive potentials and the substrate of P-type MOSFETs to negative potentials? We will address that post midterm when we talk about these topics in detail, inshallah. So that concludes the lecture for today, and next time we will talk about the IV characteristics of MOSFETs, and also we will talk about the capacitances of associated with MOSFETs. Right, see you next time. Take care. Bye.